And now, Dr. Daniel Heredero. Before being doctor, we call him Danny, but, you know, status, please. From CITSEA UPC, they did great work, and he will explain properly, as he has done during these years in any place that we have been together. So, let's start.
Okay, thank you very much, Santi. I would like to say, first of all, thanks, but not only thanks to be there, to be here sharing what we have achieved during these 3 years, but also to trust in us to be part of, we can say, the IDPR solution. We are CITSEA, we are a research center that belongs to the Polytechnical University of Catalonia. This means that we are not a company, but in the end we are engineers. We are engineers that believe in trying to find solutions to achieve a better world. And as an example, this morning we have listened something about the B2G. We participated in another project 7 years ago, developing the first B2G unit in Spain that was able to discharge an electrical vehicle to the grid following CHAdeMO protocol. And now I think that we can be proud to say that we are part of the IDPR solution, as I have said, and hopefully I can say that we have developed part of the 3 first IDPR in the world. So I think that we can be proud of this work. Okay, so from our side, basically I'm going to explain a little bit the technology and some of the functionalities that we have developed to give to the IDPR the capability to follow the needs that is required for the rural area. So again, I am going to be really fast in these 3 first slides. It's only to refresh a little bit what Ramon explained this morning about the pilot area. This is what we have at the beginning of the project. We have a line directly connecting 4 electrical substations, 2 of them in Poland, the other 2 in a building. You have seen the pictures this morning. Then we have conventional transformers, switchgears, and so on. And the system started to change. And after 3 years, apart from other devices, I also want to remark that the IDPR, it's not only the power electronics that I'm going to explain in the next slides. It's a mixed system that integrates different subsystems. But here in the pictures, you can see how the IDPR looks like for the 3 different pilot sections that we have used as use cases for the project. So again, we have to face with a complex situation because we want to reconfigure our electric system. We want to operate it in island or in grid-connected mode, and this will be a challenge point. So first of all, give some ideas of the conceptual device parts. The IDPR should be able to operate in 2 operation modes. One, we have called them slave and master mode. Slave modes means that we are grid-connected, so we are essentially going to compensate harmonic components, balance the system, and manage the power. At the end, we can sum up these 3 items saying that the IDPR is able to route the energy. And later on, we will see how it works. Then we have another operation mode that is the master operation mode that basically the IDPR is used to energize the system. So this means that the IDPR is able to restore, to start up the system in case of a blackout, and in this way continue to supply energy to the customers. So first of all, we have to develop a state machine, a really simple state machine, to give the information from the IDPR side and inform all the other part of the system in which operation mode or in which state the IDPR it's working. Then about the power electronics, we decided to adopt a 2-stages power electronics scheme because the IDPR can operate considering that we are going to connect a battery, a storage system, but also without a storage system. In case that we consider that we're going to connect a battery, we want to be as flexible as possible. So this means that we want to connect different technologies, different voltage levels. The first stage is used for boost the voltage. So we will have the required voltage to operate the AC side at the end is the important part. Also to remark that we have adopted a 4-wire AC converter, and this means that we will have the flexibility and the capability to operate each phase independently, and this will give the capability to support any of the different operation or requirements that the ADPR will need. The ADPR is a power electronic device that is connected in series with the substation, and basically it's divided into main parts. One is what we have called the central control cell that basically integrates the main switches, protective devices, pre-charged circuits, and so on. And then we have the current source controlled power cell that is the power electronic itself that includes the power devices, driver circuits, cooling systems, DC links, and so on. The important part, we have developed an IDPR, we have developed power electronics, but thinking that we have to be beyond the state of the art. We cannot use obsolete technology. In that sense, we have thought the design of the IDPR thinking in efficiency, and to do that, we have used new semiconductors, new materials, and advanced control strategies. Here we have some examples for the cooling system. We have used spare spin fin configuration. In that sense, we can reduce the volume required from 1.5 to 1/4 than the other extruded alternatives, conventional alternatives. We have also included the use of a full silicon carbide commercial 6-pack unit for the semiconductors. This means that we can use high switching frequency, even increasing the efficiency from 5 to 8% in comparison with conventional silicon options, and we can reduce the volume required by a factor of 2 or 3. Also, for example, for interconnecting the IDPR with the electrical system, we need some coupling filters, and to construct and design them, we have adopted also advanced materials that we can reduce the losses, or maintaining the losses, we can reduce the volume. So here we have a picture of how the IDPR looks 2 years ago. This is the first big version. This is for lab. For lab, we need a big device because we need to connect our proofs and so on to test that all is working properly. But to give some figures, this first version is about 35 kilowatts. The size is 700 per 300 and 300.5 millimeters approximately. We have only including an inductive filter of 400 microhenries, a big inductive coupling filter, but this was quite heavy. We are talking about 80 kilos. So we have done work during these years trying to evolve this first version, trying to reduce the size and also enhance the capabilities of the IDPR. In that sense, we have developed the second version. This is the version that currently is installed in the pilot area. We are talking now about 22 kilowatts. This is just one cell, so this only integrates one silicon carbide module, but the size is reduced. We have used a rack-mounted enclosure in order to facilitate the assembly in case that we want to parallelize the system. We have also included not only the inductive filter, but also the capacitive filter. Remember that the IDPR has to work not only connected, but also disconnected. So this means that we need to control the voltage somehow, and to do that, we need a capacity. So in this case, this capacity is also included in the same stack, let's say. we have also developed some extra printed circuit boards also mounted in a rack to include some extra DC link to stabilize the inner DC link of the system in case of necessary. And we have obtained, for the same amount of power, comparing them, a reducing weight of 30 kilos. So for the first iteration, I think that it's quite good. Then splitting the different parts that integrates the power electronics and how it's controlled. Here there are the different components that integrates the IDPR. We have a master control board that has been developed for the project based on a DSP that has embedded two cores. One is a DSP itself that is directly used for the control of the power electronics, and then one ARM that is used just for communications. So we can separate the part of exchanging data with the part of controlling the currents and voltage itself. Then this master control board has also integrated the state machine of the system and manages the set points for the slave control board. Each slave control board, it's able to manage up to 2 cells. One cell is what we can see here on the slide. There are 3 different pictures of the same unit. Then for the 2 units that considers battery, we have included a lithium battery of 320 volts and 60 amps hour. And then here also the extra DC link. So this is just to give some idea of what technology is included in the IDPR, but I also want to show the important part that it's what is capable to do, what is able to do the IDPR. Here we can see 2 different schemes only to represent that we have 2 solutions. One that includes the battery, so we need the 2 power stages that I explained before. One to adapt the voltage at the battery side, and the other one to operate, to interface our IDPR with the grid. And in case that we just use an IDPR without battery, we just need 1 power stage. Well, this is a funny result of the project. We have developed for the project advanced control algorithms, and one of them is that we have formulated a new type of controller. Okay, this is a particular case. This is a lab case. For sure, we cannot inject a Batman in the rural system. Okay, but this is just to show the capabilities of what we have developed. In that sense, we're able to follow really strange waveforms. So this means that we can compensate, we can do almost whatever we want in terms of current or voltage. Okay, real results. These first ones are from the lab, but then we will see a video from the pilot area. The first thing, functional test. We want that the IDPR has the capability to compensate reactive power. So this means that, for example, before we install an IDPR, this green line represents the voltage, this light blue line represents the current. Here we can see that both waveforms are shifted 90 degrees. So after the incorporation of the IDPR is the responsible to inject this reactive power, and this means that the line is discharged from this responsibility. So we are using the current infrastructure to what we need. It's for what it was designed at the beginning, is to transmit active power, not reactive. Then another thing, and this maybe represents in the best way the concept of routing. Imagine that we have a system. These are the 3 line currents. 2 phases are with almost no load, and one is with some current. And the IDPR has the capability to say, okay, I'm going to consume in a balanced way the currents from the line side, from the DSO side, and then I'm going to supply just what I need at the load side. So this means that we are routing the energy. We are, for example, we need 10 amps of current in phase A, but we are consuming from the grid side 3.3 approximately amps per phase. Another example, in grid connected mode also, we can have an aggregated load that at the end suppose a really nonlinear load. And this is an extreme situation. But for example, imagine that we have a load with this profile that represents about 61% of THD in terms of current. The IDPR is able to supply all the harmonic components except the 50 Hertz component, that this last component is supplied directly by the grid. So the grid sees only less than 1% of distortion, and all the distorted components are supplied by the IDPR. This is all for the grid-connected mode, but what about the grid-disconnected mode? These are also in lab, but for example, in this case, these three waveforms represent the three voltages, and then we connect, in the worst case, just more or less at the peak in terms of current, a heavy load. The IDPR is based on power electronics, so this means that we don't have the inertia, the mechanical inertia that we will have if we are generating with a rotatory machine. So we need to supply that current in a really fast way in terms of voltage, because the load, in other way, will see a dip or a sag depending on if we connect or we disconnect the load. So as you can see here, we are able to support that heavy consumption just with a really fast transient in terms of voltage. So this is good because we are supplying inertia in terms of current. What about nonlinear loads? This is a more extreme case. Then the transient is a little bit longer, but in less than 2 grid cycles, we are able also to support the required voltage to continue feeding the load. One interesting case, it's something moved, but I think that I can explain it. Well, here we have a similar situation, but if we are operating the system in grid disconnected mode, we have also to ensure that in case of a short circuit or an overload, the system will be able to reduce the voltage accordingly to some preconfigured current, because in that sense, the conventional protective elements will be responsible to disconnect the fault. In that sense, for example, before enable some overload control algorithms that we have implemented, we have 230 volts in each phase. So in case of a fault, we are supplying always the fault, but after activating it, the phase, well, it's the green. I think that it's a little bit difficult to see, but there is a reduction in terms of amplitude. We reduce from 230 to 215 volts, and we supply only 41 amps. That was the current that has been pre-configured as an overload or short circuit current. So in that sense, the responsibility is moved to the protective elements, because the IDPR is able to maintain the same behavior expected as a conventional generator. Then I think that this video is quite interesting. Here, this is an oscilloscope video. It's not nice as the ones that we have seen, but I think that it's quite impressive. These are 3 real currents that we have in Berger one day. This part is a zoom in of the top one. Here, these 3 waveforms are current, so you can see that they are really distorted. It contains harmonic components, and well, about reactive you cannot see because there are any voltage plotted, but you can imagine. What I'm going to do now, no va el vídeo. Pues no. Com? No. Well, it's a pity because it was a really interesting video, but no vaig. Okay, well, this is some other results, also extracting data from the pilot. For example, here we have the voltages, here we have the currents, and we are enable and disabling different capabilities. For example, harmonic current compensation, or some others. In the first case, we have we are compensating the reactive power and balancing, but you can see that even doing these two, well, enabling these two capabilities is not enough, because if you take a look, the currents are quite ugly. Then if we just compensate the harmonic components, the current waveform is more sinusoidal, but they are unbalanced. And if we combine all the possibilities in grid-connected mode, they are quite sinusoidal. If we analyze a little bit the data, before connecting the IDPR, the initial situation in terms of power factor, it's that one phase is close to 1, but the other ones are far away. After the connection of the IDPR capabilities, each phase is approximately 1, so this is a good result. In terms of harmonic distortion, the first situation before the connection of the IDPR is that we have, in terms of voltage, up to 2.5% of distortion, and in terms of current, about 70. After the connection of the IDPR, we reduce the current distortion to 6.5, and we have also correct a little bit the voltage. So this means to increase the quality of service that we are supplying to the rural consumers. And in terms of balancing, before the connection of the IDPR, we have one phase that it's only contributing in terms of current of about 80%, and after the connection, the system is totally balanced, and each phase is contributing with 1/3 of the total required power. So one thing that I want also to remark is that the IDPR is a flexible solution. We have developed some power electronics that has to be adapted to each one of the different sections that are included in the pilot area. Berger has a transformer of 25 kilowatts, but it's a 230 volts face-to-face system. Planayonga also has a transformer of 25 kilowatts, but it's a conventional 400 face-to-face volts. And Artigas is a more powerful substation. It considers a 100 kilowatt power stage, that is this one of here. And finally, Artigas also consider batteries, and this, in this case, is integrated by four power modules. So at the end, we want to go towards the digital grid, but how the IDPR can contribute to this digitalization? In terms of efficiency, it allows to include forecasting, and we have assumed the usage of leading-edge technologies. In terms of flexibility and coordination, because we can connect the IDPR to different AC, but also DC systems and technology, and also the IDPR, and this is really important, will allow to help the integration of renewable energies to the system. In terms of management, because we can operate the system in grid, but also in grid disconnected mode, and reconfigure the system according to the capabilities at each moment. And finally, in terms of functionalities, The ADPR can help to give some functionalities as can be time shifting, route the energy, as I have shown, short circuit management, harmonic compensation, balancing the phases, dispatching reactive, peak shaving, and so on, and so on, and so on. Okay, the ADPR, we can say that it's the muscle of the system, but we have the brain, it's the global EMS, also with part of the local EMS, but somehow we need the nerves that will help to transmit the set points, the operation configuration, and so on. And my colleague Ramon will explain this part, that you will see that the SCADA system has all things needed for the integration of all this intelligence and transmit this intelligence to the ADPR itself.